So this time we're taking a look at section 16.5. which deals with curl and divergence. So we're going to be taking a look at a vector field F. Let's say that F is represented as F equals Pi plus Qj plus Rk. So this is a vector field on R3. So suppose that this is vector field on R3 and that the partial derivatives of P, Q, and R all exist. And then we can define the curl of F So, curl of F is the vector field on R3. And that's defined by the following. So the I component is going to be the partial of R with respect to Y minus partial of Q with respect to Z. Your J component is going to be the partial of P with respect to Z minus partial R with respect to X. And then finally, your K component will be the partial of Q with respect to X minus partial P with respect to Y. Alright, so that's how we define the curl of F. So let's consider the vector differential operator del. Now, the way that this works is that you'll have I times partial with respect to X, J times partial with respect to Y, K times partial with respect to Z. And so, if you take a look at del F, for some function little f that we have, we're going to have that's the same thing as I times partial of f with respect to x plus j times partial f with respect to y plus k times partial of f with respect to z. Now, we typically write this as partial f with respect to x times I, so partial f with respect to y times j, partial f with respect to z times k. So if you think about the cross product of del with, let's say, this vector field F, we can do our determinant form here, where we'll have the I, J, and K on the top. And then we'll have partial with respect to x, partial with respect to y, partial with respect to z in the middle. And then the vector field F has components P, Q, and R. So those go along the bottom. And so if you think about what's going on here, you could do a cofactor expansion, for example, and if we expand along the top row, then I is going to get multiplied by the 2 by 2 determinant you get when you delete the row in the column containing I. So that'll leave us with the 2 by 2 matrix that we have in the bottom right corner. So you have the determinant of that matrix times I. Then we would have minus, and then take away the row in the column containing J. You'll have partial with respect to x, partial with respect to z, and P and R on the bottom. No E times J. And then plus the 2 by 2 determinant that we get when we delete the row in the column containing K. That gives us the 2 by 2. That's in the bottom left corner. But if you think about what this gives us, well, when we take the determinant here, we'll have partial of R with respect to Y minus partial of Q with respect to Z. That'll be our I component. And then we'll have minus partial R with respect to X minus partial P with respect to Z. And then we'll have partial Q with respect to X minus partial P with respect to Y. And that'll be our K component. But notice something here. The I component is partial R with respect to Y minus partial Q with respect to Z. Same I component we had here in the curl of F. We have minus partial R with respect to X minus partial P with respect to Z. But another way to write that would be partial P with respect to Z minus partial R with respect to X, which is precisely our J component in the curl of F. And then partial Q with respect to X minus partial P with respect to Y, same as the K component in the curl of F. So this is another way that we can represent the curl of F. And so with that in mind, let's take a look at an example. So in this example, let's say we have vector field F of x, y, z, of x, z, I, plus x, y, z, j. Minus y squared k. So for this vector field, we're going to find the curl of F. Right. So let's set this up. If we think of this as del cross F, we're going to curl of F equal to we have our first two rows, and then third row, I've got a little more room here. There we go. And then the third row will have xz, and then xyz, and then a negative y squared. So we're just putting in the p, q, and r as they're given in this vector field here. And so notice that what I've written down here, if you think about cofactor expansion along the top row, I is going to get multiplied by the 2 by 2 determinant that you get from these entries here. So that's precisely what we're seeing. So we have minus, and then we delete the row and column containing j. So j is going to get multiplied by negative the determinant, the 2 by 2 matrix involving this, 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 and that. And then we'll add the determinant of the 2 by 2 that you get when you delete the row and the column containing k. So that'll give us these 4 entries. So now it's a matter of actually calculating these different partial derivatives. And so when we take a look at the I component, we're going to be taking the partial with respect to y of negative y squared, but that's going to give us a negative 2y. And then we have to subtract the partial with respect to z of xyz. That means we're subtracting xy. And then we'll have minus, and now we'll take the partial of negative y squared with respect to x. Well, that gives us 0. And then we'll have minus the partial with respect to z of xz. Well, that's x. Subtract x away. And then we'll take a look at adding. And then we take the determinant here, partial with respect to x of xyz. Well, that's going to be the same thing as yz. And then minus partial of xz with respect to y, that's going to be 0. And so if you think about what this gives us, we have the curl of f of negative 2y minus xy times I. Then minus a negative x gives us plus x, and this times j, and then plus yzk. Alright, so that is our curl. So if you're thinking about what the curl actually represents, well, basically what we are measuring has to do with rotations. And so let's suppose you have a vector field f, and maybe it's some sort of velocity field in fluid flow, then particles near a point xyz are going to tend to rotate about the axis that points in the direction of the curl of f. And the length of the curl of f is going to be a measure of how quickly those particles are going to move around that axis. So let's take a look at the theorem. Let's make some room first. So we have f as a function of 3 variables. It has continuous second order partial derivatives. Curl gradient of f is 0 vector. Alright, so we're accustomed to taking a look at the curl of, let's say, f as del cross f. But here we have the curl of del little f. And so one way that we can think about that is as del cross with del little f. And so if we think about what that would actually give us, let's go ahead and set up our determinant form here. Partial with respect to x, partial with respect to y, partial with respect to z given del, partial f with respect to x, partial f with respect to y, partial f with respect to z, along the bottom row. And so if we do our cofactor expansion, what's going to happen is we'll get, delete the row on the column containing I, you'll have this 2 by 2 determinant here. Have minus, and then take away the row in the column containing j. Plus, and then take away the row in the column containing k. But what you may notice is that when you go to simplify, you're going to get a bunch of second order mixed partials. But if you notice, with each of these differences, second order partial derivatives involve the same variables. Here y and z, here x and z, here x and y. And by Clairaut's theorem, because we know we have these continuous second order partial derivatives, we know that this difference is going to be 0, this difference is 0, this difference is 0, which means that our result is the 0 vector. And one note I want to make here is that if F is a conservative vector field, the curl of F is the zero vector. So with that note, let's take a look at the following example. So here we're going to show that the vector field f of x, y, z equals, and it's the same one from the example that we did earlier. So xzi plus xyzj minus y squared k. I'm going to show that is not conservative. Now, remember, in this example, we actually found the curl of f. So, from the previous example, we know that curl of f is negative 2y minus xy times I plus xj plus yzk. And that is not the zero vector. So as a result, f is not conservative. All right. So let's take a look at the following theorem. So let's say that f is a vector field that's defined on all of R3. And let's say that component functions have continuous partial derivatives. And let's also have that the curl of f is a zero vector. And it turns out that f is a conservative vector field. All right. So let's take a look at an example. This example is actually going to have two parts. so for part A, we're going to have f of x, y, z. It's y squared z cubed I. Plus 2xyz cubed j. Plus 3xy squared z squared k. So we're going to show that this is a conservative vector field. And then once we've shown that this is a conservative vector field, we're going to find a function little f such that big F is equal to gradient little f. All right. So the way we're going to go about this is we're going to take a look at curl of f, del cross f, so we'll have these familiar top two rows. And then the bottom row, we're going to have y squared z cubed, 2xy z cubed, and a 3xy squared z squared. And so if we think about what that gives us, take away the row in the column containing I, we'll have these four showing up. And minus, take away the row in the column containing J, we have these four showing up. Take away the row and column containing K, and these four show up. All right. And so we've got the 2 by 2 that we're going to evaluate here. And so we take the partial with respect to y of 3xy squared z squared. Well, that's going to be 3x times 2y times z squared, or 6xyz squared. And we'll subtract partial with respect to z of 2xyz cubed. Well, that'll be a 2xy times 3z squared. That'll be a 6xy z squared then. And notice what happens. We get 0 for the I component. And then subtract, we'll take the partial with respect to x of 3x y squared z squared. That'll be a 3 y squared z squared. And then we take away partial with respect to z of y squared z cubed. Well, that's going to be y squared times 3z squared, or 3y squared z squared, and again, we see that we'll get 0, this time for the j component. And then we'll have partial with respect to x of 2xyz cubed, that's going to be a 2yz cubed. And then we'll subtract partial with respect to y of y squared z cubed, that'll be 2y times z cubed. And we get 0 for the k component. So that means that the curl of f is a 0 vector, and the curl of f is 0. Then that indicates we have a conservative vector field. All right. We also know the domain of f is defined on all of R3, so put those together and you know that f is conservative. And now that we know that f is conservative, let's try to find a little f such that big F is the gradient of little f. So we'll need a little bit of room for that. Okay, so for part B, we're going to be finding a little f such that big F is gradient of little f. And the way we go about doing this is the same way we went about it a couple sections ago. So we're going to start out, we know that if we have this little f, and we know we do because we just showed that big F is conservative, then partial little f with respect to x is going to need to be y squared z cubed. Partial little f with respect to y is 2xy z cubed. Partial little f with respect to z is 3xy squared z squared. So we'll start out with partial little f with respect to x. It's going to be y squared z cubed. But that means if we integrate with respect to x, it means that f of xyz is going to be x y squared z cubed plus some sort of constant, which is going to be actually a function of y and z, because we know if we take the partial of this thing with respect to x, we're just going to get 0. This is treated as a constant if you're looking at taking partial with respect to x. And so we have at least part of what we're looking for, but we're going to need to narrow down what this g of yz is. Now, one thing we can do is we can evaluate the partial of f with respect to y directly from what we're seeing here. And if we do that, we'll have an x times 2y times z cubed. That'll be a 2xy z cubed, and then we'll have plus partial with respect to y of g of yz. Now, we also know the partial f with respect to y is the same as the j component here. So that's 2xy z cubed. And so if partial of f with respect to y is equal to this and it's equal to that, then that means these two expressions must be equal to each other. And so we set these expressions equal to each other, and then if we subtract 2xyz cubed from both sides, then we'll get partial with respect to y of g of yz is equal to 0. But then that just implies that g of yz is going to be a constant, which in this case we can think of as h of z, because z will certainly be treated as a constant if you're taking partial with respect to y. And so when we think about this form we had for f of xyz before, we can update it. We'll have xy squared z cubed plus h of z. Now, when we take a look at partial of f with respect to z, we can evaluate that directly. We'll have xy squared times 3z squared, or a 3xy squared z squared, plus h prime of z. But we also know that partial f with respect to z is going to be 3xy squared z squared. So what we find is that we have two expressions for partial f with respect to z. So this and this are the two expressions. They must be equal to each other. So you'll have a 3xy squared z squared plus h prime of z is equal to 3xy squared z squared. Now if we subtract 3xy squared z squared from both sides, we get h prime of z is equal to 0, which means that h of z is equal to some constant k. So now we know what h of z looks like, we can plug it in. And we know that the left of xyz is equal to xy squared z cubed plus h of z, which is k. There you have it. There's your function f, little f. All right, so with that, let's take a look at the other part to this section, divergence. And so we, a little bit earlier, took a look at what curl was about. And we start taking a look at divergence. Basically, the divergence is going to measure tendency of, let's say you have F is a vector field's velocity of a fluid. Then F is going to measure the tendency of the fluid to diverge from a point. So big F of xyz would be a measure of tendency of the fluid to diverge from the point xyz. And so the way we're going to define divergence is as follows. So once again, we're looking at F as Pi plus Qj plus Rk is a vector field on R3. And let's say that the partial P with respect to x, partial Q with respect to y, and partial R with respect to z all exist. Then we can define the divergence of F. It's going to be a function of three variables. Defined as follows. divergence of f is partial p with respect to x plus partial q with respect to y plus partial r with respect to z. Now if you think about that, we had a little representation for the curl of f as del cross f. Turns out the divergence of f is going to be del dot f. So we're going to be taking a look at an example in which we find divergence of a vector field. And this will be a familiar example. Xz I plus xyzj minus y squared k. We're going to find divergence of f. Alright, so del dot f. Now remember the way it's defined here. Partial p with respect to x plus partial q with respect to y plus partial r with respect to z. P is x times z, q is x, y, z, r is negative y squared. So divergence of f give me the partial with respect to x of xz plus partial with respect to y of x, y, z plus partial with respect to z of negative y squared. And so when we take partial with respect to x of xz, we get z. Take the partial with respect to y of xyz, we get xz. You take the partial with respect to z of negative y squared, and you get 0. And so the divergence of f is z plus xz. All right. So let's take a look at the following theorem. So let's say f equals pi plus qj plus rk is a vector field on R3. And p, q, and r have continuous second order partial derivatives. Then if we take the divergence of the curl of f, we get 0. Alright, so if we think about the divergence of the curl of f, well, remember the curl of f is del cross f. And what we've been saying is that, for example, the divergence of f is del dot f. So I guess the divergence of del cross f would be del dotted with Go across that. See, what we know is that we know what del cross f looks like. That's your curl of f. And so we'll have partial r with respect to y minus partial q with respect to z. There's I. Plus partial p with respect to z minus partial r with respect to x, there's j, plus partial q with respect to x minus partial p with respect to y times k. We also know what del looks like. Partial with respect to x, I. Partial with respect to y, j, is partial with respect to z, k. And so if you think about taking the dot product of this and this, then what this really turns into is we're going to be taking the partial with respect to x of this thing, plus partial with respect to y of this thing, plus partial with respect to z of this thing. And this gives us a bunch of second order partials. Now notice that these mixed partials actually come in pairs if you think about it, because you take a look at this and this. These two mixed partials are equal, so their difference is going to be 0. We know they're equal because of Clairaut's theorem. This is going to cancel with that. These two also match up. Those mixed partials are equal, so their difference is going to be 0. And these mixed partials are equal to each other, so their difference is going to be 0, which means everything just canceled out. Divergence of the curl of f is 0. All right. So let's take a look. Following example. We'll show that vector field. We're going to go back to a familiar example. F of x, y, z is equal to x, z, I plus x, y, z, j minus y squared k. We're going to show that that cannot be written as the curl of another vector field. Now, basically what we're trying to show here is that f is not the same thing as the curl of j. For for any vector field G. So let's go back to the divergence of F. We know that was Z plus XZ. And so that means the divergence of F is not equal to 0. But let's suppose that F is equal to the curl of some G. Well, then that would mean that the divergence of the curl of G would have to be 0. And that's by our previous theorem here. But then that contradicts the fact that the divergence of F isn't 0. And so, as a result, F is not the curl of another vector field. All right. So to finish out this section, we're going to be taking a look at some vector forms of Green's theorem. All right, some vector forms of Green's theorem. So what we're going to be taking a look at, we're going to have a plane region D, we're going to have a boundary curve, which we're calling C, and the functions P and Q. Say these all satisfy the hypotheses of Green's theorem. And we're going to take a look at a vector field F equals Pi plus Qj. Now, we know that the line integral along C of F is equal to line integral along C, p dx plus q dy. But let's think about what would happen if we were to regard F as a vector or a vector field in 3 space, just with the k component being equal to 0. So if we were to do that, then we would say that the curl of f is going to be the following. You'll have your I, j, and k along the top. Familiar middle row as well. And then you'd have p of xy, q of xy, and 0 along the bottom. But if you think about what that would actually give you, if you were to do cofactor expansion, let's say, then take away the row and column containing I, you're now down to this 2 by 2 matrix. Take the determinant. Partial with respect to y of 0 is going to be 0, so that product, or this is going to be 0. And then partial with respect to z of q of xy is going to be 0, so the I component would just be 0. J component, take away the row and the column containing j. Partial with respect to x of 0 is 0. Partial with respect to z of p of xy is 0, so your j component is going to be 0 as well. K component, take away the row and the column containing k, and what you're going to get is partial with respect to x of, well, basically it's just partial of q with respect to x. Right, partial q with respect to x minus partial p with respect to y. So that's going to be your curl of f. Now, if you were to take a look at the curl of f, dotted with k, then what you're going to get is partial q with respect to x minus partial p with respect to y times k, dotted with k. But think about what the components of k look like. You got 0, 0, and 1. Components of the curl of f, 0, 0, and partial q with respect to x minus partial p with respect to y. So you take the dot product, you're getting partial q with respect to x minus partial p with respect to y times 1. Well, that's just your partial q with respect to x minus your partial of p with respect to y. But this looks pretty familiar, especially from the last section, because we were saying that our line integral of f along c was equal to the double integral over d of this difference. And so we can rewrite this as this line integral of f along c is equal to double integral over d of the curl of f dot k. dA. All right, so what this actually tells us is that the line integral of the tangential component of f along c can be expressed as the double integral of the vertical component of the curl of f over the region that c encloses. Question is, can we derive a similar formula involving the normal component of f? So let's try that. Let's see. Be given by r of t, x of ti plus y of t, j. And we'll have t ranging from a to b. Now, you may recall from several chapters ago this idea of a unit tangent vector. And so when we take a look at unit tangent vector, that's the same thing as 1 over magnitude of r prime of t times r prime of t. But what are the components of r prime of t? Well, x prime of t and y prime of t. So another way that you could write big T is as follows. You could write big T as x prime of t over magnitude of r prime psi. That's y prime of t over magnitude of r prime times j. Now, you could take a look at what's called the outward unit normal vector to C and call that n of t. But you can actually show that this will be the same as y prime of t over r prime times I minus x prime of t over magnitude of r prime times j. So once again, y prime of t over magnitude of r prime times I minus x prime of t over magnitude of r prime times j. And let's face it, if you were to take, it makes sense that this would be a normal vector, because if you were to take the dot product of this with the unit tangent vector, you would in fact get 0. And so we think about the line integral along C. But this time we're going to take a look at the dot product of f and n with respect to arc length. Now, what exactly is that going to give us? Well, you would have, this is the same as, well, you have the integral from a to b, so we're going to end up writing this integral in terms of t. You'd have f dot n of t times the magnitude of r prime of t dt. After all, that's what your ds is, magnitude of r prime of t dt. But let's think about what f dot n would actually look like. Well, f has components p of xy, q of xj. N has these components. And so if you were to put all this together, then what you would end up with is this would be the integral from a to b. Well, the first component of f times the first component of n, you would have p of x of t, y of t, times y prime of t over magnitude of r prime of t. Then you'd have minus because of the minus here. And then you'd have your q of x of t, y of t. Times x prime of t. Over magnitude of r prime of t. So that's going to be your f dot n of t, but then that's multiplied by the magnitude of r prime of t. And if you take a close look, what you may notice is that the magnitude of r prime of t you have here is going to reduce out with the magnitude of r prime of t's that you see in the denominators here. So as a result, what we're going to get is that this is the integral from a to b. Well, you've got your p of x of t, y of t, y prime of t dt minus q of x of t y of t times x prime of t dt. But that's pretty neat, because when you take a look at it, what you notice is that this is going to be the same thing as the line integral log c. Well, you got p, and then y prime of t dt. Okay, y prime of t dt. What is that? Well, y prime of t is derivative y with respect to t times dt gives you dy. And then we'll have a minus q. And then x prime of t dt is going to be dx. So you get a p dy minus q dx. But according to Green's theorem, this will be equivalent to double integral over d, but we got to figure out of what. Well, let's think about it for a moment. We're accustomed to seeing line integral of p dx plus q dy. That's what we're accustomed to seeing, line integral along c of p dx plus q dy. And we know that that's the same thing as double integral over d, partial q with respect to x minus partial p with respect to y, dA. What you have to remember here is that we have a p dy up here, we have a q dy down here. We have a negative q dx up here, we have a p dx here. So in the statement of Green's theorem that we're accustomed to, it turns out that negative q is actually playing the same role that p does here. And p is playing the same role that q does here. And so as a result, when we take a look at partial q with respect to x, we're taking a look at the partial of whatever is next to the dy here with respect to x. So that would be the partial of p with respect to x in this case. And then we would be subtracting the partial of whatever is by the dx here with respect to y. Well, negative q is by the dx here. So we would be subtracting a negative partial q with respect to y. That's the same thing as adding partial q with respect to y. But partial p with respect to x plus partial q with respect to y is the divergence of f. And so what we get is that this line integral of f dot n along c with respect to arc length is equal to the double integral over d, divergence of f, dA. And so what this means is that the line integral of the normal component of f along c can be represented as the double integral of the divergence of f over the region the c bounds. And so that finishes section 16.5. Now some recommended exercises 1, 3, 5, 13, and 15.